So let's talk about how we can use the different visual variables to symbolize grids. Because grids are made up of pixels or picture elements or little squares or grid cells, we can't really change their shape or size or orientation very easily without completely distorting the image that it is. But what we can change with grids is the color. And unlike other things that we do in GIS where we typically talk about the HSV color space, usually with grids we're working with the RGB color space, or the red, green, blue color space. So we're basically typically assigning colors based on red, green, or blue with values varying from 0 to 255, and then we're combining those colors in order to get a color grid image. So let's talk about how we do that. We can do that with imagery, and probably the two biggest kinds of imagery we use in GIS are aerial photographs and satellite imagery. Aerial photographs can either be digital imagery that we've taken with digital cameras, or it can be old film-based photographs that were actually taken from a camera on a plane or a kite or some other thing that was up in the air. Satellite imagery is typically always digital imagery. We're collecting data from sensors on satellites, and then that's what we're bringing down to Earth and displaying as maps. So we'll look at some examples of these, but first, kind of the other big category are these data grids. And these data grids can be anything from elevation or temperature, rainfall, any sort of field that we would typically map where values are changing constantly. So we want to account for all of those variations by assigning different values to each of the different grid cells. Let's start though with the imagery. This is a typical aerial imagery, and it's overlain on a map here. This aerial imagery can be captured in two different ways. One is through film, and once again, this is mostly from historical imagery. So a plane would fly, it would have a camera on it, it would take a picture, and then that film image would be put in its proper location on a map. But the other way that this image could be taken is as a digital image. And if it's a digital image, typically the way those sensors work is that they measure various parts of the electromagnetic spectrum. So basically different parts of what color is coming towards them. Some of them measure in the red area, some measure in the green area, and some measure in the blue area. So we might get three different grids that we're going to combine into this color photo. And if we think about it, if this red can have values from 0 to 265, this green can have values to 0 to 265, and the blue can have values of 0 to 265. In order to get a true color image, all we have to do is whatever value we recorded as blue, we assign to the color blue. Any value we recorded as green, we assign to the color green. Any value we recorded as red, we assign to the color red. And we get out a true color digital image. With satellite imagery, we can do the same. We can come up with a true color digital image, or we could make something like the one on the right here, and you may have seen examples like this before. Sometimes this is called a false color satellite image or a infrared satellite image, and you may have also seen infrared photographs that are taken in a similar way. Let's talk about how these two things work. So when a satellite's up in the sky, it's measuring different parts of the electromagnetic spectrum. So it has different sensors on it. Each one of these boxes is meant to represent what's being measured by a different sensor, including light we can't even see over here in the near infrared part of the electromagnetic spectrum. But let's say, for example, now it's just we're taking the values in the blue part of the electromagnetic, what were measured in the blue part of the electromagnetic spectrum, the green part, and the red part here. Then we can just combine those in the same way. We assign red to red, green to green, and blue to blue, and we get an image like we see here, where the colors are what we would see with our eye. However, we don't have to assign colors in that way. Remember, there's a lot of different bands that are being read from these satellites. And for example, if we assigned red, if we assign the near infrared, what was measured in something that's invisible to our eye, to the color red for display, and then we represented what was measured in the red portion to green, and what was measured in the green portion to blue, then we get one of these false color composite images like we see here. And so basically what we're doing again is the same data that was collected, but now we have a new part of the electromagnetic spectrum that we measure, the near infrared, and we're assigning that, even though this wavelength is invisible to our eye, for purposes of symbology, we're just assigning it to red here. And then the red is being assigned to green and the green to blue, and then we get this false color composite image here. The reason that we do this is because the near infrared gives us some useful information that we can't see with our eye, such as where the healthy green vegetation is, because chlorophyll really shows up with this near infrared. If we have any sort of grid, though, we can just assign color values to it however we want. We probably want to have some sort of color scheme where there's a lighter and a darker end. We can go use some of the different rainbow colors, like this one uses yellow, green, and blue. But in general, it starts out with the lightest colors, gets darker through the greens, and gets the darkest into the blues here. This is meant to represent annual rainfall in the state of Montana. And we can clearly see where the driest areas here are out in eastern Montana, and then where the wettest areas are up in the Rocky Mountains in western Montana. And we try to make color schemes that roughly approximate, maybe this looks more deserty to people, this looks like it's greened up a little from getting a little more rainfall, and this just kind of looks cloudy and wet to people. So we also try to use colors not just to go through a progression of lighter to darker, but also, if we can, to make it meaningful to what people are seeing. And this is true in this map here. It's not really going from lighter to darker. It kind of has this dark area in the middle and then a darker area over here. But this is an elevation map, and this elevation map is made from a digital elevation model, but it's made by assigning hue and saturation colors based on what the elevation is here. And then it's also applying hill shading, which is basically just a three-dimensional representation of what the terrain looks like in the shades of gray. So this is no longer using the RGB color model. This is using the HSV color model. The hue and saturation are assigned by elevation, as we see in the legend here, and the value, or the grayscale, or the darkness, is assigned based on hill shading.